Welcome to this problem walkthrough. Today, we'll explore problem number 2170, minimum operations to make the array alternating. In this session, we'll break down the problem, analyze the brute force approach, and discuss its complexities. Let's dive in. In this problem, we are tasked with transforming a given integer array into an alternating array. An array is considered alternating if every element at an even index is different from the element immediately following it at an odd index. To achieve this, we are allowed to perform operations where we change any element in the array to any integer of our choice. Our goal is to determine the minimum number of such operations required to make the array alternating. The input is a single integer array nums, and the output is the minimum number of operations needed. For example, if the input array is 31324A3, our task is to calculate how many changes are required to make it alternating. In the first example, the output for the array 313243 is 3. Here's why: we can transform the array into 313131 to make it alternating. Notice that all even-indexed positions 0, 2, 4 hold the value 3, while all odd-indexed positions 1, 3, 5 alternate with the value 1. To achieve this, 3 operations are needed. First, we change nums 3 from 2 to 1. Next, we change nums 4 from 4 to 3. Finally, we change nums 5 from 3 to 1. This results in a total of 3 operations to make the array alternating. In the second example, the input array is 12222 and the output is 2. To make the array alternating, we can transform it into 12121. Here, the even indices 0, 2, 4 hold the value 1, while the odd indices 1, 3 hold the value 2. To achieve this, we need 2 operations. First, we change nums 2 from 2 to 1. Then, we change nums 4 from 2 to 1. With just these 2 changes, the array becomes alternating. In the third example, the array is 111111 and the output is 3. To make it alternating, we could transform it into 121212. Here, the even indices 0, 2, 4 retain the value 1, while the odd indices 1, 3, 5 hold the value 2. Accomplishing this requires 3 operations. We change nums 1 from 1 to 2, nums 3 from 1 to 2, and nums 5 from 1 to 2. With these 3 changes, the array becomes alternating. This demonstrates how we minimize the operations while ensuring the array satisfies the conditions. Finally, let's consider some constraints and edge cases. The length of the array ranges from 1 to 100,000, and each element in the array can take a value between 1 and 10,000. Special cases to keep in mind include arrays of length 1, which are already alternating and require no operations. Similarly, arrays where all elements are the same need careful handling, as we must determine the optimal replacements to minimize operations. Additionally, arrays that already alternate but not in a consistent pattern may still require changes to meet the exact definition of alternating. These considerations are key to solving the problem efficiently. To solve this problem, we first considered a brute force approach. The intuition behind this method is simple: for every even-indexed position in the array, we try all possible values that ensure alternation with the adjacent odd-indexed positions. This guarantees that the resulting array will alternate correctly. The steps involve iterating through all even indices in the array, testing all possible values that would alternate appropriately with their neighboring odd indices, and then counting the number of changes required to achieve this alternation. We repeat this process for the odd indices as well, and finally, we return the minimum number of changes required across all configurations. While this method is straightforward and ensures correctness, it is computationally expensive. The nested iterations required to test all configurations result in a time complexity of O n superscript 2, which makes it impractical for larger arrays. On the bright side, it has a low space complexity of O(1), as we do not use any additional data structures. The brute force approach, while simple, has significant trade-offs. Its major downside is inefficiency for larger inputs due to the lack of any optimization or pattern recognition. This leads us to a more efficient strategy, an optimized frequency-based solution. The key insight here is that instead of testing all possible configurations, we can analyze the frequency of values at even and odd indices separately. By identifying the most common values in each group, we can minimize the number of changes needed to achieve an alternating array. The problem boils down to ensuring that the values at even indices differ from those at odd indices, which is essential for maintaining alternation. The optimal solution focuses on maximizing the frequency of these values, as this directly minimizes the number of changes required. If the most frequent values at even and odd indices are the same, we can resolve this conflict by choosing the second most frequent value for one of the groups. This ensures that the alternation condition is satisfied while keeping the number of changes as low as possible. To implement the frequency-based approach, we follow these steps. First, we count the frequencies of all numbers at even indices and odd indices separately. This gives us a clear idea of the most common values in each group. Next, we identify the top two most frequent numbers for both even and odd indices. This step is crucial for handling cases where the most frequent values in both groups are the same. Once we have these top frequencies, we compute the minimum number of operations required for each valid pairing of these values while ensuring alternation. Finally, we return the minimum operations across all pairings. This approach is highly efficient, with a time complexity of O(n), since we only need to iterate through the array a few times to count frequencies and process the top values. The space complexity is O(k), where k represents the number of unique values in the array, as we store the frequency counts. This method is not only faster than brute force but also avoids redundant computations, making it well suited for large arrays. While it does require additional space to store the frequency maps, this cost is negligible compared to the computational savings. After analyzing both approaches, we chose the optimized frequency-based solution for its efficiency and scalability. While the brute force method is simple and guarantees correctness, it is computationally impractical for larger arrays, especially when the input size can go up to 10,000 elements. The frequency-based solution, on the other hand, leverages the structure of the problem to minimize unnecessary computations. By focusing on the most frequent values at even and odd indices, it systematically reduces the number of operations needed. This approach is highly efficient, with a time complexity of O(n), which makes it suitable for large inputs. It also scales well in handling edge cases, such as arrays with only a few unique values, and avoids the redundant work inherent in the brute force method. While it does require extra space for frequency maps, the trade-off is well worth it given the significant reduction in runtime. In conclusion, this method provides the right balance between efficiency, simplicity, and correctness, making it the ideal choice for solving this problem effectively. To solve this problem, we need to rearrange an array so it forms an alternating sequence where elements at even indices are smaller than their adjacent odd-indexed elements. For example, the array should follow a pattern like this: _0a_1a_2a_3a_4, and so on. This creates a wave-like pattern where values alternate between peaks and valleys. To achieve this, our goal is to ensure that for every index I, if I is even, the element at I is smaller than the one at I plus 1, and if I is odd, the element at I is greater than the one at I plus 1. A key observation here is that we can maintain this alternation by iterating through the array and swapping adjacent elements whenever the condition is violated. By doing this, we can solve the problem efficiently in linear time, or O(n), since each swap directly resolves a local violation of the alternation pattern. The algorithm begins by iterating through the array, specifically from index 0 to n2. For each pair of adjacent elements, we check whether they satisfy the alternation conditions. If the current index I is even, we ensure that the element at I is less than the one at I plus 1. If this condition is not met, we swap the two elements. Similarly, if the index I is odd, we ensure that the element at I is greater than the one at I plus 1. Again, if this condition is violated, we swap the elements. For the swapping process, we use a temporary variable to hold one of the values, ensuring no data is lost. Once all pairs have been processed, the array will conform to the desired alternation pattern, and we can simply return the modified array. This straightforward design ensures that each violation is resolved locally, which guarantees the global correctness of the solution. Let's walk through an example to see the algorithm in action. Consider the input array 3, 5, 2, 1, 6, 4, starting at index 0, we check whether 3 is less than 5. Since this condition is satisfied, no swap is needed. At index 1, we check whether 5 is greater than 2, and again, no swap is needed. Moving to index 2, we see that 2 is not less than 1, which violates the condition, so we swap these two elements. The array now becomes 3, 5, 1, 2, 6, 4. At index 3, we check whether 2 is greater than 6, which is not true, so another swap is performed, resulting in 3, 5, 1, 6, 2, 4. Finally, at index 4, we verify whether 2 is less than 4, which is correct, so no further swaps are needed. The output is 3, 5, 1, 6, 2, 4. This example highlights the greedy approach of fixing violations locally, ensuring that the array adheres to the alternation pattern by the end of the single traversal. This algorithm relies heavily on the simplicity of working directly with the input array. Since the array is modified in place, no additional data structures are required beyond a temporary variable used for swapping elements. Addressing edge cases is also important. If the array is empty, we simply return it as is. If the array contains just one element, it already satisfies the condition. Similarly, if the array is already alternating, no swaps are performed. Lastly, if all elements in the array are equal, the alternation condition is trivially satisfied, so no changes are necessary. In terms of complexity, the algorithm is highly efficient. It runs in O(n) time since we perform a single traversal of the array, and it requires O(1) space because no extra memory is allocated. This combination of in-place modification and linear runtime makes the solution optimal for this problem. Here, we start by importing the counter class from the collections module, which will help us efficiently count the frequency of elements. In the solution class, the minimum operations method begins by handling a simple edge case. If the array has one or no elements, it's already alternating, so we return 0. Next, we split the array into two groups, one containing elements at even indices and the other containing elements at odd indices. Using the counter, we determine the frequency of each number in these two groups. Afterward, we find the two most common elements in the even and odd indexed groups. To ensure there are no index errors, we pad the results with a placeholder value in case there are fewer than two unique elements. Finally, we extract the most common and the second most common elements along with their counts for both the even and odd index groups. This setup prepares us for the logic to calculate the minimum operations needed to make the array alternating. Now, we consider two possible scenarios. In the first case, the most frequent elements in the even and odd positions are distinct. Here, we can directly calculate the result by subtracting the combined frequencies of these two elements from the total length of the array. This gives the minimum number of changes required. In the second case, the most frequent elements in both positions are the same. To resolve this, we need to use the second most common element in one of the groups. We calculate two options, one where we change the odd index group to use its second most common element, and another where we adjust the even index group similarly. The result will be the minimum of these two options, as we want the fewest changes possible. This completes the logic for determining the minimum operations required. Here, we start by defining our solution class and the main function, minimum operations. The first thing we check is a base case. If the array has one or no elements, it's already alternating, so no operations are needed. Returning 0 in this case ensures we handle these trivial scenarios efficiently. Next, we initialize two frequency maps, even counts and odd counts, to track the occurrences of numbers at even and odd indices respectively. As we iterate through the array, we populate these maps by incrementing the count for each number based on whether its index is even or odd. This separation of counts allows us to analyze the frequency of numbers in the two groups independently. Finally, we use a helper method, getTop2, to identify the two most frequent elements and their counts for the even indices. These will be stored in variables like even1 count, even2, and even2 count, which we'll use to calculate the minimum number of operations later. Now, we apply the same process to the odd indices by calling getTop2 for the odd counts map. This gives us the two most frequent numbers and their counts for the odd positions, which we store in variables like odd1 count, odd2, and odd2 count. With this information, we can evaluate two key cases. In the first case, the most common elements for even and odd positions are different. When this happens, we can simply add their counts together and subtract from the array length to determine how many elements need to be changed. In the second case, the most common elements for even and odd positions are the same. This overlap means we must consider two alternatives: either we change the odd group to use the second most common odd element, or we change the even group to use the second most common even element. We calculate the operations needed for both options and return the smaller of the two values. This ensures we minimize the changes required to make the array alternating. Finally, we look at the implementation of the helper method, getTop2, which is responsible for finding the two most frequent elements in a given frequency map. We initialize variables to track the top two elements and their counts. As we iterate through the map entries, we compare the current count with the highest count seen so far. If the current count exceeds the highest, we update the second highest to match the previous highest, and then update the highest to the current count and its associated number. If the current count is not the highest but is greater than the second highest, we update the second highest accordingly. By the end of the loop, we have the two most frequent elements and their counts, which we return as an array. This method ensures that we can efficiently analyze the frequency data needed for our main solution logic. To solve this problem, we first need to separate the array into two groups: elements at even indices and elements at odd indices. For the array 3, 1, 3, 2, 4, 2, the even-indexed elements are 3, 3, 4, which correspond to indices 0, 2, and 4, and the odd-indexed elements are 1, 2, 2, corresponding to indices 1, 3, and 5. Next, we count the occurrences of each number within these two groups. For the even-indexed elements, the counts are 3, 2, 4, 1, meaning 3 appears twice and 4 appears once. For the odd-indexed elements, the counts are 2, 2, 1, 1, meaning 2 appears twice and 1 appears once. Based on these counts, we identify the two most common elements in each group. For the even-indexed group, the most common elements are 3, with a count of 2, and 4, with a count of 1. For the odd-indexed group, the most common elements are 2, with a count of 2, and 1, with a count of 1. The next step is to determine if the most common elements from both groups are different. In this case, the most common number in the even group is 3, and in the odd group, it is 2. Since 3 and 2 are distinct, their counts can be added together directly to calculate the result. To calculate the minimum operations needed, we start by determining the total number of elements in the array, which is 6. The formula for operations is the total number of elements minus the sum of the counts of the most common elements from the even and odd groups. Here, the most common even element, 3, has a count of 2, and the most common odd element, 2, also has a count of 2. Plugging these into the formula, we get operations equal to 6 minus the sum of 2 and 2, which is 6 minus 4 is equal to 2. Therefore, the minimum number of operations needed to make the array alternating is 2. Now, let's move on to a second example with the array 1, 2, 2, 1, 1, 2. First, we split the array into even and odd indexed elements. The even indexed elements are 1, 2, 1, and the odd indexed elements are 2, 1, 2. Then, we count the occurrences in each group. For the even group, the counts are 1, 2, 2, 1, while for the odd group, the counts are 2, 2, 1, 1. In this example, we again determine the two most common elements in each group. For the even indexed group, the most common elements are 1, with a count of 2, and 2, with a count of 1. For the odd indexed group, the most common elements are 2, with a count of 2, and 1, with a count of 1. We then check if the most common elements in the two groups are different. Here, the most common even element is 1, and the most common odd element is 2. Since 1 and 2 are different, their counts can be summed directly. The total length of the array is 6, and the formula for operations is the total number of elements minus the sum of the counts of the most common elements. Substituting the counts, we get 6 minus open parenthesis 2 plus 2 close parenthesis, which equals 2. This means that 2 operations are required to make this array alternating. In this third example, the array is 1, 1, 1, 1, 1, 1. First, we split the array into even and odd indexed elements. The even indexed elements are 1, 1, 1, and the odd indexed elements are also 1, 1, 1. Next, we count the occurrences in each group. For both the even and odd groups, the counts are 1, 3, since all elements are 1. Now, we determine the two most common elements in each group. For the even group, the most common element is 1, with a count of 3, and since there is no second most common element, we append none, 0. The same applies to the odd group, resulting in the most common element being 1, with a count of 3, and the second most common being none, 0. In this case, the most common elements from both the even and odd groups are the same, as both groups have 1 as the most common element with a count of 3. Since the most common elements are not different, we need to consider alternative options. We compute two scenarios. The first option is to change the odd group to its second most common element. The formula is the total number of elements minus the sum of the most common count from the even group and the second most common count from the odd group. Substituting the values, we get 6 minus open parenthesis 3 plus 0 close parenthesis is equal to 3. The second option is to change the even group to its second most common element. Here, the formula is the total number of elements minus the sum of the second most common count from the even group and the most common count from the odd group. Substituting the values, we get 6 minus open parenthesis 0 plus 3 close parenthesis is equal to 3. The minimum number of operations is the smaller of these two, which is 3. Thus, 3 operations are required to make this array alternating. To analyze the time complexity of our solution, we start by breaking down the major operations involved. First, we split the elements of the array into two separate groups, those at even indices and those at odd indices. This is done by iterating through the array with a step of 2, which requires a single pass over all elements, resulting in a time complexity of O(n). Next, we calculate the frequency of elements in these two subarrays using the counter class. This operation is dependent on the number of unique elements in the subarray, denoted as k, and since the total size of the array is n, the counting step is bounded by O(n). Finally, to determine the two most common elements in each subarray, we use the most common 2 method. This involves sorting the frequency dictionary to find the top two elements, which has a complexity of k log k. Since k, the number of unique elements, is at most n, this step is n log en. Now, moving on to the constant time operations in our solution. Extracting the counts of the most common and second most common elements is an O(1) operation because we're only accessing pre-computed values. Similarly, the final calculations to determine the minimum operations involve simple arithmetic and conditional checks, which are also O(1). When we combine all these steps, the dominant term in the time complexity is the n log n, contributed by the most common 2 operation. Thus, the overall time complexity of the solution is n log n. Shifting focus to space complexity, the primary contributors are the counter objects used to store frequencies for the even and odd indexed elements. In the worst case, where all elements in the array are unique, the size of each counter object is proportional to the number of elements in the corresponding subarray. Since the total number of elements is n, the combined space used by these counters is n. In addition to the frequency counters, we also consider the space required for other components of the solution. The most common 2 method returns a list containing at most 2 tuples for both even and odd subarrays, which adds a constant O(1) space. We also have temporary variables such as even1 count, and others, which are scalars and require O(1) space as well. Importantly, the solution doesn't rely on any additional data structures or recursive calls, meaning there are no hidden space costs. Overall, the space complexity is dominated by the storage needed for the counter objects, resulting in a total space complexity of O(n). Let's compare this optimized approach to a brute force solution. A naive method would involve iterating over all possible combinations of values for the even and odd positions in calculating the number of changes required to make the array alternating for each combination. This would require n squared * k squared time, where n is the size of the array and k is the number of unique elements, making it highly impractical for larger inputs. In contrast, the optimized solution leverages the counter class for efficient frequency computation and uses the most common 2 method to quickly identify the top candidates for even and odd positions. By focusing on frequency analysis and minimizing unnecessary iterations, the optimized solution achieves a significantly better time complexity of O(n*log n and a space complexity of O(n), making it far more efficient and scalable. Finally, let's analyze the best, average, and worst-case scenarios for this solution. In the best-case scenario, the most common elements in the even and odd positions are already distinct, minimizing the number of changes required. However, the algorithm still performs frequency counting and most _common operations, so the time complexity remains O(n*log n). In the worst-case scenario, the array contains the maximum number of unique elements, maximizing the size of the frequency counters. Despite this, the time complexity doesn't change because the operations depend linearly on the input size and logarithmically on the number of unique elements. Mathematically, the dominant term O(n*log n arises from the sorting operation in most _common, too, which is unavoidable even in the worst case. Space complexity remains O(n), as it depends on the storage for frequency counters, which is directly proportional to the input size. This consistency and complexity across all cases highlights the robustness of the optimized approach. One of the most common mistakes when solving this problem is misunderstanding the problem statement itself. For example, it's crucial to recognize that the array must alternate based on specific indices odd and even. Failing to clarify this point can lead to solutions that don't actually meet the requirements. Make sure to carefully analyze the constraints and consider edge cases before you start coding. Another issue is relying too much on brute force. While brute force may be a good way to explore the problem initially, it's not efficient and can hurt your performance during interviews. Instead, focus on how the constraints can help optimize your approach. Indexing errors are another frequent pitfall. When working with alternating indices, it's easy to confuse odd and even positions, especially in languages with zero-based indexing like Python. Always double-check your loops and pay attention to how indices are being handled. Lastly, don't ignore edge cases. For instance, arrays with only one element, or arrays where all elements are identical, can easily break your solution if not explicitly addressed. Testing against these scenarios is crucial for building a robust implementation. Now, another important consideration is time complexity. Some solutions might work well for smaller test cases but become inefficient as the input size grows. For example, a solution with O(n)² complexity can quickly become impractical for larger arrays, such as when n exceeds 100,000. Always evaluate the scalability of your approach and aim for an efficient solution. In terms of interview strategy, recognizing patterns and problems is key. Alternating arrays, zigzag patterns, or other index-based conditions often require a similar mindset of carefully analyzing indices and constraints. If you can identify these recurring themes, it becomes much easier to devise an effective solution. Additionally, start by exploring the problem with brute force, but aim to refine your solution as you go. Interviewers appreciate when you demonstrate an ability to iterate and optimize. It's also valuable to communicate trade-offs. If you begin with a less efficient approach, explain why it's necessary as a starting point and how you plan to improve it. Finally, always test your solution against edge cases, such as empty arrays, arrays with identical values, or extreme input sizes. This not only ensures robustness but also shows your attention to detail. This problem is closely related to a few others you might encounter on LeetCode. For example, LeetCode 324, Wiggle Sort 2, and LeetCode 280, Wiggle Sort, both involve creating arrays that follow specific alternating patterns. Similarly, LeetCode 75, Sort Colors, introduces the concept of efficiently sorting elements into different groups, which can be helpful when thinking about partitioning arrays for alternating patterns. Additionally, LeetCode 852, Peak Index in a Mountain Array, deals with analyzing the structure of an array to identify specific conditions, which is another skill that can transfer to solving alternating array problems. Exploring these related problems can deepen your understanding of the patterns and techniques often used in this category. When it comes to alternative approaches, one of the most optimal methods is a greedy approach. Instead of iterating through all possible configurations, you can directly construct the alternating array. For example, place smaller elements at even indices and larger elements at odd indices. This reduces the time complexity to O(n)log n if sorting is required, or even O(n) if the array is already sorted. However, this approach requires careful handling of indices to ensure the pattern is maintained. Another option is the two-pointer technique. Here, you split the array into two groups, such as smaller and larger elements, and then merge them in an alternating pattern. This method is efficient if the array is already sorted, but pre-processing like sorting might still add O and log n time complexity. Finally, there's the in-place swapping method. This approach modifies the array in place, ensuring that odd-indexed elements are smaller than their neighbors and even-indexed elements are larger. While it's space-efficient with O(1) space complexity, it can be tricky to implement without introducing bugs. Each of these methods has trade-offs, so choose the one that best fits the constraints and requirements of the problem. Great job following along. We reviewed the brute force approach to solve this problem and its key aspects. Remember, while brute force can be a good starting point, optimization is the next step. Thanks for watching, and I encourage you to keep practicing. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!